Okay, we're live. Hey, Bill.
How's it going, Chris?
Yeah, not too bad. So today we're looking at the synthesizing the rope model and surface tension gravity to try and bridge the two models. See if there's any compatibility between them, and if so, where that lies. Uh,
Okay. I can
so
synthesize for you my side of the story.
okay, that's fair enough. Yeah, start
Okay.
there.
The way I look at it, I always start at language. We need to start at language because science is about language. In other words, you need to explain a theory, you had better get your words right. That's one issue. The second issue there related to that is that physics cannot be done without objects, without things. If we wipe everything from the universe, what's happening, what's going on, nothing has occurred. There's no experiment you can run, nothing you can observe, et cetera, et cetera. So you need to have objects. And for that, you need to define the word object, and no one has done so in the last 10,000 years. You would think that the first word that a mathematical physicist, has to define is the word object is if he's going to explain a theory to someone else. We're not talking about describing mathematically. We don't need the numbers there. We don't need the variables. What we absolutely need is the objects. What objects are part of your theory, of your mechanism, right, that you're going to propose for example, gravity, right? And what I'm saying is you need to define the word object, and we define it completely different than the usage that everybody has out there. Everybody out there has see and touch, essentially. And they say an object is that which you can see or touch. We're saying that's an irrational definition. You cannot use that in science. You cannot use that in physics. What you absolutely must have is a definition that you can use consistently. And for that, we define it as that which has shape. So an object is that which has shape. Not all objects can be seen or touched. And, what I'm saying there essentially is that, if it has to have shape in order to be an object, now you have to point to it. You have to say, look, this is the object I'm going to use for my theory. For example, in the case of gravity, you want to explain what is the mechanism. And I'm saying that gravity is mediated by a rope-like mechanism, a mediator that looks more or less like a rope, a pair of twine threads, okay? And so we have any two atoms, my fingers there, my hands, right? Any two atoms are bound by a physical entity that we cannot see or touch, which has the appearance, the configuration of a rope, two twine threads, DNA-like, And now we can explain pull because we have a mediator. It's a physical mediator. This is not an abstraction. This is not a concept. It's a physical object. Now we can explain gravity because now we have this atom tied to that one. And we say that, for example, any object that falls to the center of the earth, why does it fall to the center of the earth? Very, very simple kindergarten stuff. Every atom, you take one hydrogen atom, and that hydrogen atom is connected to every atom on earth. So I don't care where that atom is. It could be a mile away, 2 miles away, 100 miles away from the earth. Every atom on earth is bound to that atom. That means that you have gazillions of these ropes converging upon that atom. The closer that atom gets to the earth, the more the ropes fan out and the faster the thing goes. That's why we have the acceleration of gravity. You have more what I call independent or effective ropes acting on that atom. The closer it is, the more they separate, the more ropes act independently. The farther the atom is from the earth, the more the ropes come together and you have almost a single coaxial and gravity is weak. So we're saying that's the mechanism that underlies especially Newton's gravitational equation. And that's essentially it. That's in a nutshell what we're proposing. The only other thing we can add is that the same rope that serves as the mediator of gravity, which is, for pulling, that same rope, the torsion along the rope is what we call light. Okay, so light is not a transverse wave. It's not a standing wave. It's a torsion wave. It's a 3D wave. That's why it's so fast. Nothing beats a torsion wave. That's one issue. The other one is it explains, why the velocity of light is a constant. And C equals frequency times wavelength. In other words, frequency and wavelength are inversely proportional. Why? And here you can see the physical explanation for that. You have how many links there? Maybe 3 links. And the more you torque it, the more links you have, and each link is shorter. And the more you untorque it, the longer the links are, and you have fewer links. Frequency times wavelength. So we are able to explain not only the constancy of the speed of light, why it's so fast, but also use that same mediator to merge light with gravity. Gravity being the pull of any 2 atoms. That's in a nutshell the introduction.
Right. Yeah. So that's it's an interesting point about the torsion on the ropes. That's kind of that might be a good place to start in terms of a sort of synthesis between the 2 models. And maybe an even more basic one would be the idea that you have light, it can travel in both directions at the same time in the rope model. Right. And that's interesting. I mean, I think the last time we spoke, we brought up Zeno's paradox, which is obviously something from ancient Greece, that kind of lineage. So, and then there's an interesting researcher, I don't know if you're aware of him, or no, I'm sure you are, Rupert Sheldrake.
Yeah, I'm familiar with Sheldrake.
Right, and so he's written a lot of books, but there was one of them that he wrote, and I think it had quite a bit to do with psychics, So, but I think towards the end of the book, he had a section on whether or not the speed of light is a constant, because because they kept in the early days they kept measuring it at different speeds, and then but they knew that they had to set light at a constant speed. So according to him, he says what they did was they bend it essentially to the meter, so it was impossible to get a different speed for light.
Well, under the rope model, it's a conceptual issue. We don't have to measure anything. We don't need to know if anyone has made any measurements and continue doing measurements here and there and finding out if there's a change in speed. What we say, very simple. C equals frequency times wavelength. That's the equation of a rope. And it has to be a constant. There's no other choice. There's no other possibility. And again, once again, frequency times wavelength means in mathematics, they look at frequency and they use the word frequency, and that gives you the idea that something is going through a given point, and you're measuring at that point how many of these goosebumps, whatever, go through it. And so they say, right. Oh, what's the frequency? And we say, you don't have to do that. You don't have to do any of that. What you're doing is torquing in situ, and all you have to look at frequency times wavelength being frequency, the number of links. Wavelength, the number of the size or the length of a link. And then, yes, you can see why little c has to be a constant, has no other choice. It's a conceptual issue. The fewer links you have, the longer they are. And the more you torque the rope, frequency increases, you have more links, and each link is shorter. Period. We're done. That's how simple.
Yeah.
What we needed to do, Chris, what we needed to do these 10,000 years is identify the mediators. No one has done that. Everybody used concepts such as field and wave and vectors instead of identifying what physical object is mediating, for example, gravity. And nobody looks at that. Here you have a spoon, it falls to the floor, right? And we know that. It falls downwards, We let go and it goes down. And you say, well, why is it going down? And we're saying, if every atom of the spoon, we're going to make an assumption here, right? If every atom of the spoon is connected to every atom on Earth, we can see why the spoon has no other choice but to fall downwards. Now, every atom of the spoon is also connected to every atom of the moon. But the moon is too far away to have an influence like the Earth has over the same spoon. And so, that's another issue that.
Right. That sounds like it's related to like Mach's principle and that kind of thing.
Yeah.
they
Because
took that,
remember, you should clarify to your audience probably what Mach's principle says, and that's more or less comes from also Newton's bucket. The fact that he
yeah.
rotated the bucket, and he says, why does the water come up on the sides of the bucket when you rotate it? And the answer for that and for Mach's principle is that every star in the universe is pulling on that bucket somehow.
Uh-huh.
And you're saying, hold it, how can that be? How can the star on the other side of the moon, on the other side of the universe, be pulling on the water? And the answer is every atom of the water is connected to every atom in the universe. Now we can understand it. That's Mach's principle.
Okay. Yeah, that's interesting. So another thing that Rupert Sheldrake spoke about, he was going back to the Greeks, speaking about what they believed. And they had some kind of unusual ideas which seemed to connect to the idea of light traveling in both directions at the same time. For one thing, they thought of the sun as a giant mirror and that it wasn't actually generating the light. It was just reflecting it, which is accurate if light travels in both directions.
Which is what Galileo did, by the way. He used mirrors on two different mountains, and he shown his lantern to his buddy on the other side on the other mountain. And he said, as soon as you see the light, you open yours. And it was too fast. He didn't open never on time.
Okay.
So he said it's instantaneous. He concluded that light was instantaneous.
Okay, yeah, I think I've heard about that. And the other one was light that he mentioned was they thought light came out of people's eyes.
As what?
So Sheldrake.
I didn't understand that. Came as what?
Oh, so the ancient Greeks believed that you weren't just seeing because light was coming into your eyes. We formulated it as like corpuscles of light coming in, bouncing off things and coming into the eye, and that's how we see things. Apparently, the ancient Greeks also believed that, or it was said that in order to be able to see, light had to be coming out of a person's eyes as well.
Yeah, it's the Superman version of light. X-ray vision comes out of his eyes, goes through the walls, and sees the nude Lois Lane in the room.
Something like this. So I think those are because like that works. Like if light is traveling in both directions, then it's reasonable to you could just easily reverse it and say that we are somehow projecting reality out of our eyes as well. And maybe because there's two eyes, then there would be some sort of interference pattern, like in the double slit experiment or something, which is and then the world around you therefore is just some sort of interference pattern generated from your eyes, which is pretty interesting. So I wrote a book, and I didn't go into those two things, but I did go into a related sort of connected idea. But I think recently you sent me a bunch of references that I added to a paper, that I was calling the new rope hypothesis, or I also called it a chord hypothesis, just to kind of distinguish it a bit. But so in that paper, I'm going to share it on screen. Is that all right?
Yeah. Let's see if I can see it.
Oh, yeah. Good point. Good point. I think we'll share this window and then this part. So this is from your paper. I'll just light, neither particle nor transverse wave. Okay, so I thought this part was interesting. This whole section, obviously, and it's to do with what you've been talking about it before, I think. So reflection and how light goes through water and then bounces from the bottom or something, and then you can still see it. I'm not entirely sure I understand your point, because I understand.
Well, let me clarify that point. When you look at yourself in a pool of water, right, you can see your reflection. And that light went all the way to the bottom, and bounced back. And now the question is, let's do this with particles. The particle, photon, whatever, had to go through all that mountain of of water, right? 10 feet of water, all the
Uh-huh.
way down, hit the bottom, assuming, we're talking about particles, the photon as a particle, right? Hit the bottom and then comes through all those same atoms all the way to your eye. So it's going
Uh-huh.
300,000 kilometers per second downwards and upwards, right? Round trip. And the question is, does that make any sense? Doesn't it bounce against different molecules and ricochet and go in different directions? I mean, why would it come back up straight? If it's got all these atoms in between, you would think that all those photons get hit one way or the other, or as they like to say, they get absorbed by the different atoms in different directions. Why would that light go all the way to the bottom and back to your eyes like if nothing happened, like if there was no medium in between, no water?
Right. Yeah. I suppose the only question I have there is, when I think of a reflection, I think of it as being on the surface of the water. So are you saying that it's also from the bottom? I'm not
you
sure.
Can see your shadow on the bottom. You can see your shadow at the bottom of the pool. And in
Right.
fact, the official version is, yes, that the photon goes all the way to the bottom, hits the wall because the water is transparent, but the wall, the bottom, the floor is not transparent. So that's where the photon hits, bounces, and comes back up. And the question is, it went through 10 feet of water round trip and never encountered an atom, I mean, and
Yeah.
even let's go with your version. Let's assume it's just surface, right?
Oh, yeah.
Why would it stop there? Why wouldn't light not go right through all the way to the bottom? In fact, I'm sure that if you have someone at the bottom, he can see you too. So that light from you is going all the way to his eye, and he's lying at the bottom 10 feet underwater.
Right. And like if the water is moving, we're going to see some distortion. I mean,
no, without moving. I mean, just standing there, the water without moving at all. The question is, you got gazillions of atoms. And the question is, doesn't the photon get absorbed, or doesn't it bounce? Does it get ricocheted from one place to another? I mean, how can it go completely straight down and completely straight up through all those atoms at the speed of light, obviously?
Okay, and so what is the conventional explanation for that, or do they bother?
No, they just say that, just what I explained, that it goes through all those atoms, comes back up. And the question is, does that make any sense? That's just like, it is so, but, it doesn't make any sense to say that went through all that body of water, 10 feet of water, and reaches, untouched, essentially, the photon, and reaches back to your eye after hitting the bottom of the pool. That doesn't sound very logical, very rational.
For sure. And this kind of connects back to what we were talking about earlier about the variable speed of light, if you like, how they measured it at different speeds. Because we think of what a light ray that comes in, and let's say you have a glass of water, and it refracts, I guess, through the glass and into the water and refracts again. But then it's going to encounter all of these molecules. So, and then you can measure the speed of light in the water, and it's slower than in the air.
Absolutely not. Absolutely not, Chris. Remember something.
Okay.
How did they come up with it? Because I work with refractive index almost every day, when I was in the semiconductor industry for many years. And the issue is, what is refractive index? Refractive index is just a calculation. It's just a mathematical, gimmick. That's all it is. You're saying, okay, the angle, they look at angles, essentially. What is the angle of light in complete vacuum? Well, it's a straight line. It's 180 degree or 0 degree. It's just a straight line. But when you go through air, water, and, glass and so on, that starts bending, and they look at the angle and they say, for this angle, we get a different refractive index. We used to work, for example, with glass, SiO2, and it was 145. That's the standard in the industry. You'll find 1.5 and 1.4 out there, but we use 1.45. And the question is, what is that 1.45? Well, that's just a mathematical calculation. It's a gimmick that looks at the angle, and that's it. It's not like, it's been measured that it's slower. It's that because of the angle, they say it is slower because otherwise we wouldn't have that angle. And we say, no, that's not true. We don't have to have that. Remember, under the rope model, you have every atom connected to every atom. So when you have light, in other words, a rope connecting any two atoms, one outside the water, one inside the water or behind the glass or whatever, right? The
Yeah.
molecules there, the atoms that are connected to that other atom out there, what happens now is they re-emit the signal to the next atom. And because there's a an effect where it absorbs that impulse, it sends it at a different angle. So we don't need to change the speed of light between any two atoms. It's always the same speed, irrespective of what medium the atom belongs to. It could belong to water, to glass, to air. It doesn't matter. The point here is that the atom is sending the same signal at a different angle to another atom because of there's several causes, but one is the density of the medium, also the molecules that make up, the crystal lattice of whatever you're sending light through. All those things have a factor, have an influence over what the angle will be. But between any two atoms, light is always at the same speed. Can't change because, again, all you're changing is frequency for wavelength, and what we're under the rope model, you're changing the link length for the number of links. That's it.
Well, yeah, that's interesting because, that is basically the conventional physics point of view, though, isn't it? Because they say light is a constant. It doesn't slow down. It's always the same speed, but because it's entering into the medium, it's like coming in, it's hitting one atom or molecule, being absorbed, and then being re-emitted, and then hitting the next one. And so that process takes a certain amount of time. And that is, then if you measure that, it's going to be slower than than some other method.
Okay, but here's the $1 million question, Chris, for that. Let's assume that theory is correct, okay, that light slows down in denser media, right? No problem. Let's concede it. Now the light goes back into air or into vacuum. What speeds it up to back to 300,000?
Yeah, exactly. So that's a bit of a contradiction, isn't it? And that's not just...
They never really explained that, they kind of sweep it under the rug.
So that is, I wrote a book and I called it Siempre Bgaede. There's another title as well. It's to do with cataphysics or something. So I looked into that. So we kind of have a similar. This is a really bad diagram, but it's all I could manage at the time. So if you think of like the black part here as, in Maxwell's equation or theory, you got like a bit of magnetism creates a bit of electricity, creates a bit of magnetism, and that's the light. So the black, let's say, is magnetism, the white is electricity. And so this is kind of like your rope model again. You'd imagine these colors switching on and off, and therefore that is the propagation of light. And because if this is switching on back and forth, there's no way to tell which direction it's going. You could go this way or that way equally. So it's kind of an optical illusion, which I think is interesting to base, a theory of physics on illusions, because of, like, let's say Plato's cave or something. If the world was an illusion, then you'd expect optical illusions to be a part of its makeup somehow. But so this was my attempt to explain what's going on with light as it refracts into a glass filled with a denser medium. So the glass is not represented here, but if it was, that, like, this line here is going through the medium, and so the glass is around here. And let's say this is the light coming in, and some of it bounces off, it gets reflected. Some of it passes through, it gets refracted. And then the same thing happens on the other side, obviously, because of the, we're saying light goes both ways equally. So
now replace that now, those lines with ropes.
Yeah, that's
and all you have is there, like, all those connection points, call them atoms. Okay, so you have one rope connected to an atom there where they meet. then that one is connected to the other atom where they meet, right? And you can do the same thing with ropes. You can just torque them and have the signal go from one atom to another atom without any problem.
Yeah, that's fair. I think in this diagram, I'm intentionally leaving out the glass of water because I'm really not interested in the molecules in the water. So there would be no atoms in the picture. It's just strictly what is going on with the light. Because if out here we've got a speed of c, and in here we've got a slower speed, and then out here we have c again, we're back to the problem of how to resolve the contradiction. So my method in this case was, I mean, it's a bit hard to explain, but I think I have some sort of analogy here. It's right. So the analogy is visualize a line of workers who are passing boxes between one another in a single direction. Okay, so they're in a line and they're passing.
There's another one you have to consider, and that's the Mossbauer effect. You heard of Mossbauer? You have no recoil in the atom, and it's still emitting, a signal. And the question is, how do you do that with photons? You would think that as soon as you try to spit the photon outwards, you're going to have a recoil backwards, and that doesn't happen with a Mossbauer effect. And so they have no explanation really for that. They just said, it is so. We measured, They don't have an explanation. And I'm saying with a rope model, you don't have to move the atom. It can continue pumping because that's what torques the rope. The fact that the atom is pumping back and forth, the famous quantum jump. This balloon is expanding and contracting. So it's a little, the atom is really a tiny heart that is pumping torsion waves along the ropes. And so you don't have to have the atom move, vibrate, or anything. You can hold it still. It's still going to do its pumping and sending the torsion waves through the ropes. You don't have that with the photon because the photons would require a recoil of the atom unless they can explain it otherwise. One of the ways they do explain it is the photon is massless, so you don't need any force, any energy to push it outwards. That's how they get around that sometimes.
Okay. Yeah, that's interesting.
Yeah.
So I'll just continue on here with an attempt to explain this. I haven't looked at this in a while, but so if the boxes are being passed from one worker to the other, and it goes inside like one side of a factory and out the other. So the factory here is representing the glass of water. And the boxes are alternatively labeled E and M for electricity and magnetism, obviously. When the boxes move inside the factory, they're processed, which takes more time than it would to pass one box to another person inside the factory. It's going to slow down, obviously. And so, in the real world, this would cause the boxes to pile up on the way inside the factory, causing a traffic jam. And, so that's might be an effect we should expect to see with the light if it's slowing down as it goes in. So
why do you call it a factory?
Well, this is an analogy for what's going on with the light as it passes into the glass.
Yeah, but you would think a factory produces something, manufactures something. Is there an assembly line? What is this?
Yeah, something like that. The boxes go in, they're processed. Maybe a factory is the wrong word then, yeah. Maybe it's like a sorting office, like for a post office or something. Okay. Thanks, Bill. That's a good, clarifier there. So
now the atom is a factory under the official version of quantum mechanics version, because they're on record saying that the atom does produce these photons, this energy that comes out of the atom. And the question is, they're saying it just comes out, and the question is, does it do that eternally? Where's the energy coming from? And so the explanation is that it receives energy from incoming photons and it spits them back out. So you have a factory in that sense, where you receive and you send out, you receive and you send out. That's the way they look at photons inside an atom, how it's produced.
Great. Yeah, I've heard some different explanations, but I'm not really sure.
Because one of the questions that triggered quantum to begin with, we're talking about 1910, 1912, thereabouts. One of the questions was, why doesn't, if the electron falls back and forth and emits energy, and that energy is what we call light. Why doesn't the electron lose energy constantly and eventually spiral and fall into the center of the atom? They never explained that. To this day, we're waiting for an explanation for the question that, that triggered quantum mechanics to begin with. And we don't have an explanation for why the electron doesn't fall to the center of the atom, or why the electron doesn't spontaneously just fly away, drift away. I mean, why do we need to ionize the atom, pull it out somehow? Why does it just leave on its own? What's keeping it there? What physical entity holds it there? And they say it's the field, but field is not a physical object. Field is a concept. So we don't have a mechanism.
I think I did hear one explanation for that. I'm not, what's the word where you uphold something, or I'm not backing this or in any sense, but the explanation they gave was, how we can sit here and talk, but we're not, we don't lose mass as we speak, kind of thing. So the idea was maybe the electron is able to sort of speaking the photon, that it's just generating it in that sense, which I guess is close to your idea of a vibration, right? The shell of the atom or particle is vibrating, and then it's
vibrating in several. Let's get that right. It's vibrating in several ways. There's a vibration, you could call it a vibration, where it's just pumping back and forth. That's one vibration. So this thing is titillating, it's going, it's a little heart that's pumping torsion waves. That's one movement. The other one is vibrating back and forth, up and down and sideways. So you have 3D vibration of the entire atom, right? Which is being triggered in great measure because it's being bombarded by torsion waves from every atom in the universe. So all atoms have to be moving. I don't think you could find a single atom in the universe that's standing still. It's not only pumping, it's moving, but then it's also spinning on its axis in different directions. It's like a little, ball that's spinning on its own axis in different directions. So we have all these motions with the atom, the electron shell that encapsulates the atom, and all those have to be taken into consideration when you're analyzing what the people have measured in the past, because they say, well, we measured, we know that this is happening. Yeah, we're saying it does happen, it's just the explanation that is different. We don't have a little bead going around the nucleus, which is a bunch of balls. No, we have a membrane that encapsulates what we call the proton star. You have this what I call a sea urchin, rolled up sea urchin, all the points pointing in different directions, all the spikes pointing in different directions.
Right. Yeah. So
it's a different model of the atom. But.
Okay. So, I mean, I think I wrote this probably about 10 years ago. So, and I haven't really looked at it. But
have you published this one?
I just sort of published it online. I think it's on Amazon.
Okay.
With a bunch
because you now publish another paper, right?
Oh yeah, the recent paper that I did on.
Yeah, that's the one I was interested in. I thought that's the one you were going to cover today.
Yes, we are going to get to that. I think I know the one you're talking about. But we're just, this is still relevant to what you were talking about with the refraction and reflection. So the point about this traffic jam, and then of course if it's all slowing down in the water, and then then we're going to have a problem here as well on the other side where there's not enough boxes coming out, if you like. So, but if we,
well, that's what I'm saying, Chris. All you got to do is put two atoms there, right? Where they all meet. Yeah. Put an atom there and put another atom there, and replace that with a rope. You're done.
Right, but I'm saying we can also answer this with the point that light travels back and forth in both directions at the same time, because it is explained here within these paragraphs. So perhaps I should just read some of this. Hopefully, it won't take too long to find out where this explanation begins. So we have the beam going back and forth in different directions. So if we go back to our box analogy, imagine that the worker inside can choose boxes of either the original line of workers or for the ones. So we have a line of workers here, and then we have a line of workers here. So this one can turn away a box in this direction and send a box in. And so
you got an assembly line.
Yeah, and so the guy inside has the option to turn away a box, sending it back out.
I hate to tell you that manufacturing is dying.
Well, yeah, I guess. I mean, that's another point, Bill. That maybe that's more for the extinction thing that we're going to do.
Yeah.
Now we see that there's really is no difference between either beams, as they're both getting their boxes into the factory at an equal rate. So there's some idea here where, this person passes a box in, and then there's boxes being passed out as well. And then
let me do a little criticism of that. Okay, just my gut feeling here. Show me the picture back again. Raise it up there a little bit. It's better to see it. Okay, the question is, why are all those lines straight? Really, rectilinear is the correct one word, because you're saying those boxes are all independent, discrete units. Am I right?
Well, that's just an analogy.
Fine. But I mean, what we're talking about is photons. We're talking about discrete entities, discrete packets of energy. I don't know how you want to.
Well, if it's bits of electricity and magnetism, then how's that a photon?
Okay, so we're talking about a discrete package of energy, I guess, right? That's what they call them.
Right. Okay.
Quantum. Okay, so the question is, why do they travel rectilinearly? Why is one right behind you? Why don't they go in different direction? Why don't they go in curves? Why don't they go in a different way? What keeps them in a straight line, parallel to a straight line?
Well, isn't that the whole point of this propagating wave, where it goes a small amount of electricity creates a small amount of magnetism, and then
but see, a wave. This is a wave. I mean, this is a little solid, but you see what I'm saying? I'm moving it up and down. It's not going straight. It's going up and down, right? It's going like this, like an S.
Yeah.
And so the question is, why does a wave, right, that goes up and down, why is it going straight? And I like to give the analogy, when you're in high school or in college, you'll see the instructors give you the standing wave. So they move something up and down, right? But it's got to be connected at the other end. As long as I've got this connected at the other end, I have a straight line. But what happens when I don't have it connected at the other end? Well, you have this situation. Now you don't have a straight line. And so the question is, it's got to be connected before, at the other end, before you can do anything with it, before you can create the standing wave or anything else. And that's one of the issues, the straightness part, the rectilinear part of travel. Why do photons travel rectilinearly, one right after another in a straight line? And they never explain that. Why don't they get lost?
Yeah, it's interesting.
I mean, if they're discrete entities, they can go in any direction. Why would they follow the leader?
Right. Yeah, that is another interesting point. So basically, this is probably, I think we've covered this. So you're going to get the idea that you can work it out. It's like a code kind of thing. You can read it there. But maybe we will then move on to this other.
This is the paper you're publishing now?
Yeah, this was is this the one you're talking about, Bill?
Yeah, I think so. I think that's the one. Yeah.
Okay, great. So this is based on previous work I did with the 24 cell. And it is linked to the standard model. That's how I went about it. You could, I've been speaking to other, physicists and people interested in physics and who aren't very, they're not very bullish, if you like, on the standard model, or
they're not dogmatic,
or they don't even really think it's a good model at all. But I think, they would have their own system, which kind kind of comports with it, but just in a different way, maybe with less extra steps. So it's a simpler model, which is actually generally a good thing, I would think. But I think you could do it either way then. So I'm just trying to wonder, how are we linking this? So obviously this is kind of a new rope model because we're looking at
I like
pair
that one.
production.
One of the fellows in our group in Facebook, he did something very similar to what you see there.
Oh, right. Great. Send me a link onto that. I'd love to see it.
Yeah, you should join the group because these people are trying to find different ways of, visualizing how the universe should be working if we now go with a rope model. And what you have there is the rope model, except that what I see there, if I'm not wrong, right, you have up to 4 wires making up a single rope because they have to come from the other ropes that come in there.
Yes.
So in the center, so let me clarify. In the center, you only have 2 strands, but when it goes into the rope, it turns into 4 strands because now you have to unify one set of 2 ropes of 2 strands with the other set of 2 strands. So you got 4 on the rope and only 2 in the center. You see what I'm saying? See, if you look at the center, just a little square in the center, right? The little rectangle there, you'll see that there's only 2 strands on one side, 2 strands on the other side, but there's only 2 strands here or there. But when you go to the rope, it's 4 strands.
Yes.
Okay. So, again, this is one of the issues that was brought up because someone came up with something similar to what you're showing there. And that was one of the issues. The issue is, hold it, how many strands do we have here?
Oh, yeah, but you can go down here. And so here we've got, so obviously, like I'm saying, this is supposed to be a model for electron pair production, annihilation process. So we have a particle coming in here and a particle coming in here, and then 2 particles coming out, annihilating and being generated. And so
when
in the center
will we get rid of the particle, Chris? Tell me. We need to kill the particle.
Okay, yeah, I'm just using the language of physics so that everyone.
Well, you know why the particle? The particle, because the word particle used to be a corpuscle. That no longer is the case since quantum came around. The word particle now means number, value, amount. They're talking about a value, okay? And so they say, we're moving this value because they're not interested in the physics of it. They're interested in the mathematics of it. So they treat it as, they talk about charge or whatever unit they're going to be talking about. And what they're really moving is a number. And that's why they talk about particle. And when you say, well, what do you mean by particle? Are you talking about a grain of sand? And they'll clarify, no, that's not the case. What we're talking about is this is an amount. I mean, look at the neutrino. Neutrino was a leftover they could not explain of energy. And they said, we'll call it the neutrino. It used to be, originally they thought it was neutron, but when Chadwick came up with a neutron, they said, okay, we'll call this one the neutrino. But what is it? What is the neutrino? Is it a little ball, a little bead? No, it's not. What it is a leftover energy they could not explain, and they gave it a name, and they called that the neutrino. And when they verified that, there is always this extra energy, they say, we proved the existence of the neutrino. That's how those things work.
Oh, that's interesting. I didn't know that about, there's some connection between the word neutron and neutrino. I mean, it sounds like it.
Fermi came up with the neutrino, and they presented at a conference. But in between, what they had is Chadwick came up with the neutron. He had to name it the neutron because he says it's an uncharged particle that have more or less the mass of the proton. And so they said, well, what do we do with this other little leftover energy? We'll call it the neutrino because it's a little neutron.
Okay. Yeah, even though it doesn't really have any of the other class characteristics.
Yeah, but all these are just numbers. Dark matter is another perfect example of that. They cannot explain the mass that they would need to make the galactic rotational problem that they can answer that question. And so they said there's some mass out there, and we'll call that invisible, untouchable, unmeasurable mass. We'll call that the dark matter. And a visual light is a bunch of particles that surround the galaxy, and each little particle weighs like tons. And they had to do it that way in order to produce the effect of stars on the outside traveling fast or as fast or faster than the ones on the inside. So these are all numbers. These are not particles, the things that you can touch. It's just some mass that's out there, and they say we'll call this mass dark matter, and we'll call the extra mass that we cannot explain in our equation, we'll call it the neutrino, and so on down the line. These are all numbers. They have nothing to do with physics. This has to do with...
Yeah, I mean, I suppose, those are the kind of language issues, and perhaps they're important, but I don't want to just get too sidetracked. Just going back to the point we're making here about the center. So we can see in this diagram, it's basically the same thing. And so in the box here, this is what I'm calling, there has to be, if we have two particles like a positron and an electron annihilating, turning into a photon, then within the box here, this must be the photon. And since I already have, like if I go up here, we already have windings for both the electron, the positron, and the photon, which looks like this, then we can extend this central part out to look like this, the final image. So
I saw that in your paper. Yeah.
Right. So these are the connection zones then. And this is the photon. So and you can see there's 4 strands here. So we no longer have the problem of just 2 and 2. They're all there. And the other good thing about this then is that if we want to take the Lagrangian and integrate over this point here, which used to be a big problem. If I go back to this image, if we imagine this as electron positron annihilation, they were unable to integrate over this point because there'd be a blow up, with the because it's a singularity, and that's why they came up with string theory as a hopeful measure of eradicating that singularity. But this also does it. So I think the rope model could solve that as well.
The issue with string theory came about primarily because of gravity, the graviton. They could not explain it. They could not incorporate it within the standard model of quantum mechanics. So that's where they drifted off into new mathematics to try to give a meaning, to the graviton. But see, we have the problem with the graviton anyways, because the graviton is supposedly a discrete particle. And how do you send particles outwards and pull something inwards? Because, you have this pull force, and the question is, how do you do that with particles, with discrete grains of sand? And so this is where the problem is. They had to introduce things like the Yukawa potential, where it's a little equation where they put a negative sign in front, and they say, well, when it's negative, it's attractive. It's an attractive force. So all they did was modify Coulomb's law, and they put a negative sign in front. So it's just math. I mean, the question is whether math is physics. People ask questions like, why does this spoon fall to the floor, right? That's what the people ask. I mean, the common folk, they just say, well, why did my water bottle fall on the floor? And they don't give you an answer for that. They can give you numbers. They can say, well, I'll tell you how fast it fell. That's not the question. The question, why did it fall? What caused it to fall? And that's the answer that we're still waiting for. All these
right. In my so we're trying to join both models here, and that I have this surface tension gravity. I've already debated the differences between the two. I was talking to another sort of physicist enthusiast who's his name is John Duffield. Do you know John Duffield?
Duffield? No.
Yes.
No.
Okay, so he works a lot with electron, positron pair production, It's a different kind of model. It's also kind of similar to yours. It's in a sense, but I'll send you on a link to his website. It's called thephysicsdetective.com.
Well, one of the questions that, when you talk about annihilation, protons and primarily electrons and positrons, right? The question is, when they annihilate, what do we mean by that? What do they turn into? And when they are created, come into existence, where do they come from? I mean, from the air, from the vacuum? Is the vacuum full of all these particles? And so when they annihilate, what are we saying? That they turn into a particle that forms the vacuum? And that's when they get with these words like energy. It turned into energy, whatever that is, right? And so we have a problem because we don't have a physical mechanism for what we mean by annihilation or particle creation. You have Hawking radiation, which is, when a particle gets close to the black hole, half of it goes in, the other half comes out. And that's why you have this radiation come out. And the question is, okay, fine, let's concede. The question is, what fell in, what came out? And, are we having half a particle? Its partner fell in there. The macho guy fell in, the lady came to your eye. I mean, what are we talking about here? We lose track with all these people because they're talking about math. They're not talking about physics.
Right. Yeah. So I'm not sure if that, I'd say, on certain issues yourself and John would agree and probably disagree on others. That's normal though. So, and oddly enough, I think, we were talking about string theory there and how there was a sort of a contradiction that arose between, general relativity and then essentially Heisenberg's uncertainty principle. So you're expecting the smaller you get, the higher energies. And so you'll, instead of having like a flat surface of space, once you get down to it, the uncertainty principle is going to start it to boil essentially. So there'll be no smooth structure there. And this was a big problem, but not for all physicists, because most physicists aren't dealing in that sort of high energy realm. So they can just overlook it, was what they were thinking. But string theory said, no, let's try and get to grips with it and solve it. And so they did that through the strings and branes and all of those path integrals. But I think with surface tension gravity, it's a pull force in a flat plane. It should all equally cancel out. So I'm not sure if we're going to get that kind of a contradiction between the two things at the different energy scales, because it just doesn't matter. The further you go down, the energy is always completely canceling out. So I don't think we'd run into that problem necessarily. But then it does beg the question, is there really a graviton? And I don't think, even with the rope model that I'm proposing here, I don't even think there is a graviton thread structure, necessarily, right. Because it seems to me that it's all based on this idea of the 24 cell, which is a hypersymmetrical object, a geometric object. You can rotate it into itself in lots of different ways. It's also self-dual. And that has the 24 cell obviously has 24 cells, and because it's self-dual, it has 24 vertices. But there's a canonical vertex in the center, which is 0, 0, 0, obviously, or because it's four-dimensional, actually, it would be 4 zeros. And that's equally distant to all the other particles, which gives a sense that it interacts with them in the same way, just like gravity interacts with everything in the same way. If we exclude, even dark matter, but we don't have dark matter in this model. But yeah, so
you're going to have to account for it if you want to make some inroads, because today dark matter is a hot subject.
Yeah, well, initially, there was two sectors. There was like the boson sector in the 24 cell, and then the dual part had the fermions in it, and you could switch back and forth between them and do various matrix multiplications to get the different particles out through interactions, which was all good. within the boson sector, there was like 8 particles that were unaccounted for. So 8 vertices that had no particles assigned to them.
But they're creating new bosons every day. I mean, I've been covering some of that lately. I haven't gone to the fermions yet, but the bosons, they're creating new particles every day because they have the new particle and its antiparticle. Whatever, whenever they discover a particle, there's got to be an antiparticle, and they just put a negative sign or whatever, change one of the values, whether it's the charge or the mass or whatever, and the color, and so they have their opposites. And again, the issue there is that if 2 of these particles come together, they annihilate, whatever annihilate means. I mean, what do they turn into? Zero, zip, vacuum? I mean, I don't know.
Right. I think some of the bosons don't have antiparticles, like they are their own antiparticle, like the photon.
As far as I know, all bosons have antiparticles.
No, like think of the photon. Even the
the photon doesn't. Yeah, you're right. Gluon, I don't think there's an anti-gluon, but most of them do have antiparticles.
Yes, I think a lot of the fermions. So yeah, within the hyperspheric model as well. So that's, and even within surface tension gravity, because we're kind of looking at it's kind of an analogy with water a lot of the times. So we could have like an idea of, rather than having dark matter as a kind of space or kind of matter, it would be maybe a different kind of space that has different qualities attached to it. So instead of water, it would be more like oil. And so if you think of like when you're trying to wash like your frying pan after you've been cooking something, there's water in there obviously now. There's going to be bits of oil, and those bits of oil tend to like gather around bits of food, which is sort of like what the physicists and astronomers see when they're trying to map these globs of dark matter. And they're usually it's like a halo around galaxies, but then you'll find some galaxies without dark matter. So this is another big problem. But if it was a different kind of space, well, maybe that space, different kind of space, is not over there and is over here, and then that's perfectly valid kind of way of explaining it. But I also
Chris,
think
I'm going to have to go in a few minutes here. So if you want to wrap up something.
Yeah, so there was can I make the final point there, or do you have time for that? Yeah, I suppose I'll just say it quickly. Like you have the sphere in the hyperspheric model, and you have the projected point, and so there's going to be light coming out from all of those from the projected point in every direction, which is kind of like the rope model again, because each one could be a rope. And so that's kind of therefore a medium that the hypersphere can exist in, if you like. And then also, I think it's very much like what you were saying to do with the how do you say the thing that you mentioned at the start, which was the kind of torquing.
You're talking about the tension, the torquing, or what?
Yes, exactly. So if we look here, you have the entanglement point that you're making. So here we have the hypersphere. Let's say we have the projective point at the center, and then these are the 2 particles on the hypersphere. Then this one's spin down, this one's spin up, and then if you torque
which means clockwise, counterclockwise, by the way.
Yes, exactly. So then there's the entanglement that you're speaking of, and then we can, but in the actual model, the projective point is not at the center, it's at the top. So we just have projection, light ray, particle on the tangent plane. Then we can begin to separate the 2 particles by distance, and then even further. So they could be like on the opposite side of the universe now. But now, so this one's torquing, but now the torquing is going through another point, which could be like, some sort of gear mechanism, if you like, happening here, but we're still going to get the same entanglement process that you're talking about. So, okay, Bill, well, thanks a million for coming on anyway. And I'm going to try and stop
I'm sure we'll
sharing.
meet again, Chris.
Yeah, absolutely. If you want to come back on and do an interview, maybe with myself and Rajan next time
Okay.
on extinction, because I know we touched
You don't
on
want,
that.
you don't want to hear it. I don't want to destroy your life.
I've heard it before a couple of times. I think you did an interview with Dutton. Was it Jason? No,
Yeah,
Edward Dutton.
yeah. Well, I had a couple of them, but yeah, the issue with extinction is a subject that really concerns all of us. So it's a subject we should cover one of these days. I'm sure there's some people, at least out there, that are interested in knowing at least a different point of view. They don't have to agree, but we're presenting a point of view, and the point of view primarily is a theory of why man, our species, cannot avoid, with its intelligence, with its ability to foresee events, with all the stuff we've got, technology and so on, we cannot avoid extinction. So it's a foolproof mechanism that I'm proposing. And well, again, you have to understand the theory. So we can cover that maybe next time when we meet again.
Okay, yeah. Just before you go, actually,
Yeah.
Bill, there was two comments here. One, the first one was how rope model explain resistance. I think we might have already spoken about that, did we? Where the light going into the water, that's the resistance they're talking about.
Yeah, remember, it's not when we're talking about resistance. Like, I'm assuming he's referring to resistance in the electrical sense, where you have some blockage there, and the question is, how do we explain that? That's at the atomic level. It's not a question of rope. Okay, that's at the atomic level, and I do have a video out there explaining that. A video is worth 1,000 words, 1,000,000 words, right? Because you watch the video and it's illustrated, so you can see and say, oh, okay, this is how he explains it. So we do have an explanation for resistance, for voltage, for electricity, all those parts of electricity.
Okay, great. And the final question then, which is actually from Rajan, can we have reflection of light at the surface of the water and then refraction when light going through the water to produce after effect?
Yeah, absolutely. Both. Remember the rope is connected to an atom. That atom pumps it back through that same rope or to the sides or whatever, to other atoms in the side. And at the same time, it refracts, right? Sends it forward to other atoms that are behind it. So remember, the atom is connected to every atom. And so along every atom, every rope that's connected to that atom, you have that signal being transported outwards to different degrees, to different, different frequencies and wavelengths. And so, when the rope torques to one atom, that atom does reflect it back and to the sides, but it also retransmits it, which is what we call refraction. And we have also diffraction, which is the fact that a rope is connected to two atoms, like, in the slit experiment, you have one atom here. We'll just talk about one atom connected to two atoms at the slits, right? And those are at different angles with respect to the screen where you're going to see the fringes. And so you have this situation, hopefully I can illustrate this, where you have, as you move, you have, they're off center, like by half a length, as they move over,
Yeah. And then
you have this situation. You have this one rope is at a different angle with respect to the other, even though they came from the same atom. The signal came from the same atom. Okay.
Uh-huh.
But because one atom is on one side of the slit and the other one's on the other side of the slit, they have different locations with respect to each of the fringes on the wall. And so again, you have this situation, where they're offset. And that's what gives you the interference, constructive interference where you see the light, and destructive interference where you see the dark bands.
Okay. Right. So thanks for that explanation. If you could send us on the link, you have a Facebook group, is it?
Yeah. I'll send you a Facebook link to our group there, the
Great.
Rational Science Group.
I didn't know that existed, actually, and I'll send you on Duffield's website
Okay.
link as well. Okay, thanks a
Okay.
million, Bill, for joining us, and have a great day.
Okay, same to you. Bye-bye.